Hello everyone. In this video, we will walk through the design of cantilever beam, including the following key points covered in this video are the step-by-step determination of load calculation and the maximum factor design moments, and the design of beam tension steel reinforcement. So let's dive into our problem. Design the cantilever beam shown in the figure below to determine the required longitudinal tension reinforcement. The beam has a cross-section of 14 inches by 28 inches and it carries a uniformly distributed load of 1.2 kPa per foot dead load and 0.8 kPa per foot live load, in addition to a 5 kPa concentrated load applied at the free end. So using normal weight concrete with Fc prime is equal to 4 KSI and the reinforcing steel with Fy is equal to 60 KSI. So this is our load diagram. We have reflected all the loadings here, the dead load and the live load, uniformly distributed load, and also the 5 kPa applied at the free end of the beam. So we are given here all the parameters, dead load, live load, and the Fc prime, Fy, and the size of beam, 14 inches by 28 inches. So let's get started with our solution and break it down step by step. So first of all, we need to determine the loads, the factored uniform distributed load, and that is 1.2 dead load plus 1.6 live load. So for the factored uniform dead load and live load, we have 1.2 times 1 kPa per foot plus 1.6 times 0.8 is equal to 2.48 kPa per foot. And also we need to consider the self-weight of the beam, which is 1.2 times 14 inches times 28 inches divided by 144 times 0.15 kCF or kPa per cubic foot, and that is equal to 0.49 kPa per foot. So we have also the concentrated load, 1.2 times 5 kPa is equal to 6 kPa. So the maximum factored design moment at the support by summing moment at the face of the support here in the cantilever end, that is equal to 2.48 kPa per foot, which is coming from here, plus 0.49 kPa per foot, self-weight of the beam, times 14 feet squared over 2, plus 6 kPa times 14 feet, that is the moment arms of the concentrated load from the free end to the support of the cantilever beam, and the total is 375 kPa foot. So the letter B, determine the tension steel reinforcement. So first of all, we need to determine the steel ratio using the formula below. We have assumed tension controls so that Fs is equal to Fy and P is equal to 0.9. So before we can proceed to determine the steel ratio, we need to estimate first the effective depth of the beam. So from 28 inches minus 1.5 inches clear cover of the concrete minus 1 inch over 2, assuming that diameter of main bars is 1 inches, and that is equal to 26 inches. So this is the formula of the steel ratio. Basically, we have the general equations of the flexural formula, and if we express this into steel ratio, we will come up the quadratic equation. So to solve this one, we need to solve first the value of M and the Rm, so that we can substitute all the parameters here to get the actual steel ratio. So the M is equal to Fy over 0.85 Fc prime, that is equal to 60 KSI over 0.85 times 4 KSI, and that is equal to 17.65. And for the Rn, which is this one here, and that is equal to mu over P BD squared, where M is equal to 375 skip feet times 12 times the 1000 all over 0.9 times 14 times the effective depth of 26 squared, and that is equal to 528.3. So that's all the parameter that we need in order to calculate the still ratio. So still ratio is 1 over 0.17.65 square root of 1 minus 2 times the M and times the Rn all over Fy, which is 60,000 PSI. So the result of still ratio is equal to 0.00962. So that is the actual still ratio of the beams. So the next one is to check the minimum requirements as per the ACI 318 section 9612, and that is equal to 200 over Fy. So 200 over 60,000 PSI, that is equal to 0.0033. So this is the minimum still ratio requirement as per the code, which is less than to our actual still ratio, which is 0.00962. So there is another provision for minimum requirements, and that is equal to 3 times the square root of Fc prime over Fy, which is equal to 3 times to the square root of 4,000 psi all over 60,000 psi, and that is equal to 0.00316. So the still ratio, the one that we got is the governing one, which is ES is equal to rho BD is equal to 0.00962 times 14 times 26. So the actual still reinforcement required is equal to 3.5 square inch. So if we use number 9, and that is the area of number 9 is 1, so we need number 4 pieces, which is equal to 4 square inch, and that is greater than 3 square inch, the one that we got here, still area. So the next one is to check the tensile strain, this one here, just to double check if the steel has chilled or not. So to check that, we need to determine first the value of A. So A is equal to ES Fy over 0.85 Fc prime times B, and that is equal to 3.5 times 60 over 0.85 times 4 times 14, and that is equal to 4.41 inches. So since we have already calculated the value of A, we can now determine the value of C, which is equal to A over beta, and that is equal to 4.41 over 0.85. Our beta here is 0.85 because our strength of concrete is 4,000 psi. So if the strength of concrete is less than or equal to 4,000 psi, the value of beta is 0.85. So C is equal to 5.19, and this is the location of our neutral axis, this one here. So the next one is to determine the tensile strain by ratio and proportion. So we have the location of neutral axis, which is C, we can now determine the value of tensile strain. So to simplify the tensile strain, we will come up this equation, which is 0.003 times D minus C all over C, which is equal to 0.003, the strength of concrete, strain of concrete, times 26 minus 5.19 over 5.19, which is equal to 0.012, and that is greater than 0.005. So, which means our steel reinforcement has yield or tension control. So, our assumption of using Fy and P is equal to 0.9 is valid. So that's all, guys. If you found this video helpful, please don't forget to like and consider subscribing so that you will be updated for the next upload. Thank you very much. See you next time. Bye-bye and God bless.